In this video, we're going to take a look at the Laplace transform and how it can be used to solve differential equations. The first thing I'm going to do is let's just take a look at the Laplace transform of a particular function. I want to show you, the definition of the Laplace transform. Okay, we use this fancy L, f of t. Okay, it equals, we write it this way, 0 to infinity, e to the negative st, f of t dt. Okay, however, generally, you can't have limits of infinity, right? So to write this properly, it's the limit as t goes to infinity, 0 to t, okay? And then we write, actually, we can write it like this, f of t e to the negative st dt. So it looks like the Fourier transform, okay? So this is our definition of the Laplace transform, okay? Now, what I want to do is I want to show you just some basic derivations, okay? So now, when we apply the Laplace transform, we're going to be using a table. But I want to show you just some examples of how that table was derived. So let's look at, let me just move this over here. So let's say example number 1, okay? And we're going to look at what is the Laplace transform of 1, okay? So by definition, we have f of t equals 1. So we have the limit as t goes to infinity, okay, 0 to t. Now f of t is 1, and then we have e to the negative st dt, okay? So, well, what is the integral of e to the at? Well, it's 1 over a e to the at. So this becomes, okay, negative 1 over s e to the negative st. And again, because, well, actually, I should move this over, erase that. We should keep the limits here. Limit as t goes to infinity, 0 to t. Okay? All right, so what's next? Well, we got to sub in our values. So this becomes, let me just move it over. It becomes, we'll pull the negative 1 over s out, okay? And we have e to the negative st minus e to the 0, okay? And again, forgot to put that in here, limit as t goes off to infinity, okay? So this term, okay? Now I'm going to make a mistake just for simplicity here, but this term, e to the negative infinity, it goes to 0, okay? And e to the 0, this guy right here, is 1. So we have negative 1 over s times negative 1. Well, that means that the Laplace transform of 1 is 1 over s, okay? Now, I'm making an intentional error just to make this nice and simple for you. We'll come back and see what this actually means. Well, and in fact, here, how about let's look at it right now. Okay, so right here, the intentional error that I made here was I ignored the fact that the s is a complex number. Okay, so if we go back up here, we'll just take a look at it right now. Look, what do we have? We have that s is sigma plus j omega. Okay, and what do we have? Well, we have the limit as t goes to infinity, okay? And we're looking at this term right here, negative s t, which if we go into it, s has, okay, I'm going to erase it, I'm going to put it in here. This is sigma plus j omega times t. Well, what's that? Well, that's basically the same thing. Let me just put it here. The term that we're looking at is this guy right there, okay? Which we said goes to 0. So we have limit as t goes to infinity. And what we have is e to the negative s times e to the negative j omega. Okay, this is st and this is omega t. Okay, now the thing is that this guy right here, we know that e to the j theta is our sine cos theta plus j sine of theta. Okay, so this is a sinusoid which will never be 0. Okay, so the only thing that matters is the real part of s. Okay, so as long as sigma is greater than 0, okay, then we're taking the limit of e to the negative sigma times t, and t is going off to infinity. Okay, so this term will approach 0 as long as sigma is greater than 0. Okay, and what is sigma? Well, sigma is the real part. You see, we have, this is the real part. This is the imaginary part of s. So sigma is the real part of s greater than 0. Okay, so what we have here is it's basically a requirement, okay, on s. Okay, this is going to give us literally, it's going to give us what we call the radius of convergence. Okay, this is a radius of convergence where this Laplace transform, okay, is valid. All right. So when we look, we're going to get a table. Okay. This isn't in the table. There's a table that you can look up of all the Laplace transforms of known functions. Okay. Let's try another one, just to keep going on this. Okay, let's try a Laplace transform. Okay, let's look at this one. Let's do here Laplace transform of t. Okay, so what is the Laplace transform of t? Well, here f of t is going to be t. So what are we going to have? We're going to have here, we're going to say the limit as t goes to infinity, okay, 0 to t, okay, and now we're going to have t times e to the negative st dt. Okay, now how do we solve this? Well, in order to solve this integral right here, we have to use integration by parts, which comes from the product rule, right? The formula comes from the product rule, but the integral of u dv is equal to uv minus v du under an integral. Okay, so what we need to do is we need to select t or e to the negative st to be our u. So if we say let u equal, now I'm going to choose t because when I go du by dt, it gets simpler. Okay, if I chose e to the negative st and I take the derivative, it's just going to be negative s times e to the negative st, and it becomes more complicated, the integral. Okay, which means that du equals, let me just erase this. I'm not sure why that's not working there. Let me see here. Maybe I clicked something. me see here. Let's go back to the eraser. Get rid of that. So du equals, in this case, okay, dt. Then dv must be e to the negative st dt, okay? Which means if you integrate that, if you integrate e to the negative st dt, then v equals negative 1 over s e to the negative st. Okay? So that is, if we integrated both sides of dv equals e to the negative st dt. So v equals that. So now we can sub in our formula. So let's go back up here. So what does that mean? That means that we have limit as t goes off to infinity, okay? And u dv, this is going to be replaced by, okay, we're going to have uv, so uv is t, okay? We got the negative over s, e to the negative st, okay? Again, this is going to be from, okay, 0 to t, okay? Minus integral 0 to t of v du, which is now a simpler, okay? So we have minus negative 1 over s. So I'm going to put a plus here, put the 1 over s. I'm going to put e to the negative st, okay? And then du is dt. Okay, awesome. So let's keep going. So what does this become? Well, this becomes, I'm just going to focus on, again, this t here going to infinity applies to the whole thing. I'm going to look at the integral here. I'm going to evaluate that first. So I'm just going to rewrite this. T goes off to infinity. I'm going to keep this. We have negative t over s. I'll evaluate this in a second. I just want to keep this. I just want to evaluate the integral. It's going to be plus, okay? Integral of e to the at is 1 over a e to the at. So the integral of e to the negative s, this one's going to give, right here, it's going to give me, it's going to become a minus negative 1 over s squared, okay? And now I have e to the negative s t between 0 and tau as tau goes off, or t goes off to infinity. Now what I can do is I can, because both of these are part of the integral, I can evaluate them separately if I want. But let's go in and take a look here. So what I'm going to do, I'm going to say limit as t goes to infinity. Okay, and what am I left with? What I have is negative t over s e to the negative st minus plus, well, this is 0, okay, so that's going to go. Then minus 1 over s squared, and I've got e to the negative st, right, minus e to the 0, which is a 1. Okay. Now, as t goes off to infinity, okay, I'm gonna make that same that same mistake here, just for simplicity. If t goes off to infinity, e to the negative, it's e to the exponent of negative t is gonna be much bigger than t. So this term is gonna go to 0. Okay, and by the same token, as t goes off to infinity, this term goes to 0. So what I'm left with is literally the 1 over s squared. Okay. Now, what I want to do is I can prove to you that, I'm going to go back to the same thing here and find out, okay, what is the radius of convergence? Because, we're assuming this term. See this term again, this e to the negative s tau limit as t goes to infinity, and for good measure, let's throw in a t in there. Okay, so what happens here? Well, actually, we can ignore the t because the e to the negative st is going to grow much faster than than tau. So that infinity is going to be bigger. So I can sort of ignore that. At the end of the day, it comes down to the same thing I just did here, up here at the top. Okay, is that you take the limit as t goes off to infinity, and at the end of the day, the e to the negative j omega t term, it's a sine there. That's a sinusoid. That's never going to go to 0, right? But the e to the negative sigma tau as t goes to infinity, that term is going to tend towards 0 as t goes off to infinity. And that what's required is that sigma cannot be negative, because if sigma is negative, then e to the negative of a negative is e to the positive. So e to a positive number is going to blow up, and it's not going to converge. So what we're going to do here is we just say that the real part, okay, of S must be greater than 0 in this case. This is my radius of convergence. Okay? By the same token as what we have here. Okay? So it's basically the same thing. So we can't ignore that that fact. We need to, when we say that the Laplace transform of t is 1 over s squared, it's only valid, that equality is only valid when the real part of s, or otherwise sigma, right, is greater than 0. Otherwise, it blows up, and the equality is no longer there. All right. So now we understand how the table, the terms on a Laplace table are derived. The next thing that I want to do is I want to talk about the properties of the Laplace. I'm going to zoom in a little bit here. Of Laplace transform. Okay, properties of the Laplace transform. All right, the Laplace transform, it's a linear operator, so it follows the properties of linearity. So what we have is we have the Laplace, okay, of let me go here. Laplace of f1 of t. Oops, let me put it here. Okay. Plus f2 of t is equal to the Laplace of f1 t plus the Laplace of f2 of t. Okay. And the other property is the Laplace of c f1 of t. Okay, so this is the summing property of a linear operator, and this one is the multiplication property. So this one's going to be c times the Laplace of f1 of t. Okay. Now these two properties can be taken together. Okay, and together they're known as the principle of superposition. So principle superposition, and you can state it all. You can bring them under one property here and say that the Laplace of a times f1 of t, right, plus b times f2 of t, okay, is equal to a Laplace f1 t plus b times the Laplace f2 t. Okay, so this is our principle of superposition, and since the Laplace transform is a linear operator, it follows the two properties of linearity, which make up or can be combined into the principle of superposition. So let's take a look here at an example. Let's say that we have what I want to show here. Let's do example number 3. Okay, so find Laplace of 5 given Laplace of 1 is 1 over s, which we get from a table. Okay, so what does that mean? That means that we're going to basically use property number 2. So we're going to say from property 2. Okay, so the Laplace of 5 times 1 is equal to 5 times the Laplace of 1, which equals 5 times 1 over s, or 5 over s. Okay, so that's one of the things that we can do. All right, let's take a look at another example that uses has more in it. Okay, so example, say number 4. All right, so let's say that we have a function is, I don't know, 3 plus 6t. Okay, find the Laplace of f of t. Find the Laplace of this. So the Laplace of f of t. So here's an equation, right? We have an equation, f of t. So what we're going to do is take the Laplace of both sides. Okay, which is, now we can use on the right-hand side, we can use the principle of linearity, which is the Laplace of 3 plus the Laplace of 6, okay, or 6t, okay, which is the same thing as 3 times the Laplace of 1 plus 6 times the Laplace of, t. Okay, and we can get these from the table. This is 3, and the Laplace of 1 is 1 over s plus 6, and this is 1 over s squared. Again, from the table. Okay. All right, so this is how we can take the Laplace transform. All right. Now, let's take a look at some other, something a little more complicated than that. Okay. So example number 5. Okay. So let's say that f of t equals negative 4 t squared plus 8t plus 9. And I want the Laplace of f of t. So I'm going to take the Laplace on both sides, Laplace transform, negative 4 t squared plus 8t plus 9. All right, so what's that? Well, that is, using the linearity properties that we just saw, is the Laplace. We can do them individually. And then we can apply the second rule. And that's the same thing as, well, actually, let me go back here. It becomes negative 4 times the Laplace of t squared plus 8 times the Laplace of t plus 9 times the Laplace of 1. Okay, and now you're going to look these up in a table. Okay, and okay, we got negative 4. When you look for in the table, you have t to the n, okay, which is n factorial over t to the n plus 1. So what we have is we have n is 2, so we have 2 factorial over s to the 2 plus 1 is 3. Okay, this is straight from the table. And then we have 8 Laplace of t we just saw, which is, it's now n is 1, so this becomes 1 factorial over s to the 1 plus 1, which is s squared, plus 9, and Laplace of 1 is 1 over s. Okay, So at the end of the day, this becomes negative 4 times 2 is 8 over s to the 3 plus 8 over s squared plus 9 over s. Okay. So these are just some examples of taking the Laplace transform of a function. And again, you'll just apply the Laplace transform to the definition of the function on both sides of the equal sign. Okay, let's keep going. All right, let me go. Let's take a look at some other examples. So what I want to do next, okay, next thing I want to do is I want to show you how a Laplace transform can be used to solve differential equations, okay, or applied to both sides of the differential equation and used to solve it. Okay, so the thing we need to learn first is what is the Laplace transform of a derivative? Okay, so let me go in here. So Laplace transform of a derivative. Okay, there's an equation, but I find it hard to remember. But I'm going to show you the equation first, and I'm going to show you how I remember how to do things. So when you say Laplace transform of, this is the nth derivative of a function. That's function f of t, okay? So this is f to the n of t, okay? And the way it works, we say s to the n, okay? That's an exponent there, times the Laplace transform of f of t minus this sum here, 1 to n, s to the k minus 1, f to the n minus k, all at 0. So the Laplace transform can take a derivative as long as you know the initial value problem. So this will give you particular, if this is being applied to solve a differential equation, it'll give you the particular solutions, okay, to DE, to differential equations, ordinary differential equations. Okay, so okay, but this formula is great if you like to just use it to apply. But the way that I use it is basically let's take a look at the first few derivatives. So let's say we want the Laplace transform of f prime of t. Okay, if we apply the formula, we'll see the pattern, because there is a pattern. It becomes, okay, it's the first derivative, so it becomes s to the 1 times Laplace of f of t, okay? And then we have to subtract f at 0. This is an initial value problem, so we need to know f at 0, f prime at 0, f double prime at 0, etc. Okay, so that's the first one. If we look at the second one, f double prime of t. So if we want the Laplace transform of a second order derivative, then we have to put s to the 2. Okay, it's always the same. You start off times the Laplace of f of t. Okay, now what we're going to do, we're going to have two minuses here. Okay, and we're going to have s, okay, and it's going to be times f at 0. Okay, and then we're going to have f at 0 times prime. Okay. All right, let's go look at the next one. Applying the same formula, I'm just going to show you, because we'll see the pattern in a second. F triple prime at t, okay, is s to the 3 Laplace transform of f of t. Now, here, we're going to go, we're going to say here, go f. So actually what we can do, let me see, it's saying s to the k minus 1. So we're going to say say s squared f at 0 minus s f prime at 0, right? And minus f double prime at 0. Okay? Okay, so if we're following the same set of rules. So what do you notice? What do you notice here? Well, what you see is that, okay, we started with s to the 3. We have s squared, s to the 1, and then s to the 0, right? So the s terms decrease. Their powers of s decrease. Okay, and what do you notice here? What you notice is that the primes, right? F, the derivatives of f, go up. Derivatives increase. Okay, so the way I look at it, the way I see it is, I say s goes down. Wait, this is the way I remember it. Primes, or f primes, go up. Okay, s powers go down, f primes go up. That's how I remember to write this equation. Okay, so or you can do it the other way, depending on the order that you write these equations. You can write your primes going down, right, and s powers going up. But I think if you look at it this way, you start off with s to the 3, then you're subtracting s squared, s to the 1, s to the 0, which is just 1, and then you increase your primes basically where you need to know your initial value. Okay, so instead of remembering this formula or writing it down, I don't know, for me, I find it easier to look at this. I know I'm subtracting f at 0, but is it f at 0, f prime at 0, f double prime at 0? Well, yeah, it's going to go up as you go to the right. Okay, so s powers go down, primes go up, right? You keep increasing f prime. All right. All right, let's apply this to a differential equation now. Okay. So let's go and grab, let's find a good example here. What number are we on? Example 6 here. All right, let's go in here. And so example 6. All right, what am I going to do? I'm going to go straight to a differential equation. And actually, you know what? I'm just going to apply it to one side. We can do the whole thing. Let's say we have a differential equation that looks like this. F double prime at t minus 2 f prime at t equals 0. So we got a second order. This is a second order differential equation, which previously we did not know how to solve. So let's take a look at how we would solve this. So in order to solve this using Laplace, we need to take the Laplace transform of both sides. So whatever we do to the left-hand side of the equation, we have to do to the right. So first off, we take the Laplace transform of everything. Okay. Now, what is the Laplace transform of 0? It's 0 times the Laplace transform of 1, right? So we know the right-hand side. So anyway, I'm going to apply the linearity rules here. So this is Laplace transform of f double prime of t minus 2 times the Laplace transform of f prime at t, okay, is equal to 0 times Laplace transform of 1, which, okay, what's 0 times anything? Well, that's 0. Okay. All right. So now what we're going to do is we're going to go to these equations that are up here. Now, you never really have to memorize them. Usually you can look them up. It's not a big deal. All right. So let's do what is the Laplace transform. Oh, I forgot to indicate something. When you use these, you need to know what is f at 0, what is f prime at 0, what is f double prime at 0. So when I'm given a differential equation, I need my initial value problem to be specified. So what is f at 0? Okay, so f at 0, let's say in this case is going to be, let's make it 0. And what is f prime at 0? F prime at 0, let's make that 1. Okay, so that we can use our formula. So what is the Laplace transform of the second order derivative of f? Well, that is, right here, let me put this one down here, is going to be s squared, Laplace transform of f of t, okay, minus s, f at 0, minus f prime at 0, okay, that's the first one, minus 2 times what is the Laplace transform of f prime? Well, that's just up here. It's just s times Laplace transform f of t minus f at 0. Okay, and all of these equal 0. Okay, well, we said that f at 0 is 0. So this guy gone, this guy gone, this guy is 1. Okay, so what do we have? Well, we have s squared plus f of t minus 1 minus 2s Laplace transform of f of t, and that equals 0. Okay, what I can do, I can bring this negative 1 over to the other side. So what I have is s squared Laplace of f of t minus 2s Laplace of f of t is 1. And I can factor out the Laplace. I have Laplace f of t from both of them times s squared minus 2s is equal to 1. Awesome. Now, okay, so what I can say here is that the Laplace of the function, right, is equal to 1 over s squared minus 2s. That is my equation. So if I could take the inverse Laplace of both sides, I could get the solution to my differential equation, which is f of t. See, f of t is the solution. To the differential equation. Okay, so if I could figure out, see the reason for this, look, what is the inverse Laplace of both sides? If I do that to the left-hand side, I just need the inverse Laplace of 1 over, it's s minus 2. Right? Okay, so on the right-hand side, the inverse Laplace of the Laplace is just f of t. Okay, and on the right-hand side, what do I have? Well, I need the inverse Laplace of this equation. And now when I look in the table, I can't find anything that matches if you go and look in a Laplace table. So the next step that we need to do is we need to be able to use partial fractions. Okay, we need to expand 1 over s times s minus 2 as a partial fraction in order to solve this. So we need to figure out how to do partial fraction expansion, which should know how to do. All right, let's just review that first. So if we do that, we have what is 1 over s minus 2 Okay, that equals, now the two denominators, I'm going to have s, right? And I'm going to have s minus 2. Okay, now the denominators are first order polynomial, so the numerators are going to be a 0th order polynomial, so a constant. Okay, so now what we need to do is we say, okay, we assume that this is the solution. Okay, what are A and B? What do A and B have to be in order for this to be true? Well, that's easy. What we'll do is we multiply both sides of this equation by s times s minus 2. So that means that 1 is equal to A. Okay, the s is going to cancel, so I'm left with s minus 2 plus B. The s minus 2 now is going to cancel times s. Awesome. Okay, now there's two ways that we can solve for A and B. What we can do is you can set s equal to, so what would make this term, okay, this first term, what would make that first term 0? Well, if s equals 2, right? So we can look at it this way. Okay, let's look at method 1. Okay, what makes the first term 0? Well, if s equals 2, then the equation becomes 1 is equal to A times 0 plus B times s. Well, s is 2, so let me erase that. What is B going to be? So that means that B equals 1 over 2, right? Okay, and then if s equals 0, right, then 1 is equal to A times negative 2, right? Okay, because B times s would be 0, okay, plus 0 if you like. So that means that A is negative 1/2. Okay, that's one way to solve for A and B. Another way to solve for A and B, it's going to be the same, you're going to get the same result, but is to get the powers of s to be the same. So what we had, our equation was 1 is equal to A s minus 2A plus BS. And then collect the like powers of s, so that 1 is equal to A plus BS minus 2A. Okay, now on the left-hand side, there's no s. Literally what we have is 0s plus 1, okay? Which means that this term is 0. You see that? You see how this, and that means that this term matches with 2a. So what we have is we have that we have 1 equals negative 2a, okay, which implies that a equals negative 1/2. Okay, that's the first equation, okay, for the constant terms. And then what's the next one? The powers of s. So s to the 1. We have 0 equals a plus b. And what that means, if you have a is negative 1/2, that means that b is 1/2, positive 1/2. Okay, so both of the techniques are going to give you a and b. Okay, so now what we do is let's go in and sub. We said that 1 over this term right here, okay, is this term that we're looking at right here. Okay, so let me go back in. We want to know what is the inverse Laplace transform of 1 over s times s minus 2, this guy right here. But really, what's that? Well, that is Laplace inverse of, what do we have? Well, we have this whole thing, right? We have a over s. Well, what was a? A is negative 1/2. So we have negative 1/2, right? times 1 over s plus, okay, b, which is positive 1/2, right, times 1 over s minus 2. Okay, so this is what we have. This, now we can look in the table because you see, look, inverse Laplace transform is also linear. So what this means is that we have here, let me just put it in, is, okay, let's just do it. Okay, fancy here. Negative 1/2 1 over s plus Laplace inverse of 1/2 1 over s minus 2. Okay, I'm just going to move it over a little bit, which is the same thing as negative 1/2 Laplace, because it's linear, right? We can pull out that Laplace inverse of 1 over s plus 1/2 Laplace inverse of 1 over s minus 2. Okay, and now we can go into our table. Okay, and we can see that the inverse Laplace, this guy right here, the 1 over s, and the 1 over s minus 2. Let me see if I can get, let me go and grab you a Laplace table here and show you what I'm talking about. Okay, so here's the Laplace table. Let me bring it over to the screen here. Here's our a table of Laplace transforms. Okay, and we see that 1 over s has an inverse Laplace transform of 1. So we take that and put that right over here. Negative 1/2. This is a 1. Plus 1/2. Well, s minus 2. Let me go back and grab that table. It's right here. Okay. So if we have, see this guy right here. Okay. So that means, so a is 2. 1 over s minus 2. So a is 2. So the inverse Laplace transform is e to the 2t. Let's grab that. Let's take that out of the way. E to the 2t. So f of t, this is what f of t is. F of t, I should have put that. Let me move this over. Right? This is this right here. Right? The inverse Laplace of little Laplace is f of t. So f of t is equal to negative 1/2 plus, actually, we can, let's just say 1/2, okay, e to the 2t minus 1 would be the solution to that differential equation. Okay, so this is an example of how you can solve a differential equation by taking the Laplace transform of both sides, solving for f of t, and, well, once you solve for f of t by taking the inverse Laplace transform of both sides, you have the solution to your differential equation. Okay, all right, and all you have to do is go and look in the table with the Laplace transforms in order to do that. Okay, let's take a look at one that may be a little more complex. Okay, a differential equation that might be a little bit harder to solve, and then we'll stop there. Okay, let's see if I can find one that I like to show you. Okay. Let's grab an example here. Okay. All right, find. Let's see. Here's another example. What is it? What number are we on? Example 6. Let's go to example number 7, maybe. Okay. Right. Solve the following differential equation using Laplace, using the Laplace transform. Okay, so what we have y double prime. Let me zoom in a little bit. Y double prime plus 2y prime plus 2y equals 0. And the initial values that we have are that y at 0 equals 0 and y prime at 0 equals 1. Okay. All right. Let's go in and solve using Laplace by applying the Laplace transform to both sides of the differential equation. So what we're going to do is apply Laplace to both sides, then use the linearity rules. Okay. Going to use the linearity rules here. So we're going to say L at y double prime plus 2 L at y prime plus 2 L, 2 L at y. Okay, and we know that the Laplace of 0 is 0. Okay. All right, so now we got to go in and we have to, we need to plug in, okay, our L at y double prime. Well, what is that? Exactly, right? So let's do the first one. So L at y double prime. Okay, it's s squared Laplace of y. Okay, now we have to start taking away. And if you remember, let's go back up to the top. The powers of s go down and the primes go up. So we can start, okay? So powers of s, so we're going to say minus s to the 1, and then the next one's not going to have. And the primes, so s's are going down, the primes, okay, are going in the opposite direction, okay? Primes are going up. So we're going f at 0, okay, minus s to the 0, f prime at 0. Okay, let's go back and just make sure I went a little too far. So the double prime s squared minus s f at 0 minus f prime at 0. Okay, so you can see that I am following the same pattern here. Plus 2, okay, and this is Laplace of y prime, okay, which is s Laplace of y, right, minus, now s's are going down, so it's going to be s at 0, which is just 1, and the prime's going up, well, it's not going up that far, it's just f at 0, okay, plus 2 times Laplace of y equals 0. Okay, awesome. And we said y prime at 0 equals 0. So I say f at 0. I know I'm using the formula, which is fine. So f at 0, this is y at 0, 0. F prime at 0, this one's going to 1. F at 0 is going to 0. And we're good there. Okay, so what do we have? Let's collect all our terms. S squared Laplace of y minus 1 plus 2s Laplace of y plus 2 Laplace of y equals 0. We got to collect our terms. I'm going to bring the 1 over to the other side. So we're going to say equals 1. I'm going to factor out Laplace of y, or Laplace of f of t. It's the same thing here. So we've got the s squared plus 2s plus 2 equals 1. So we end up with Laplace of y. Okay, so we have Laplace of y is 1 over s squared plus 2s plus 2. Okay. All right, so that is, if we could take the inverse Laplace of both sides, right? We could figure out what y is, right? Y or f of t, same thing. Okay, so how do we solve this? How do we get something that we can look up in the table? Now, there's a couple of things that if you look at the table, okay, let's bring the table down here. We kind of doesn't look like anything that we have in the table just yet. So we gotta use some creativity here to try to make it look the same. So what we can do, I'm just gonna take a look. I just want to show you this equation. You see this equation here. If we could convert this equation, okay, into something that looked like, you see this s squared plus 2s plus 1 plus 1. We haven't changed anything about this equation, okay? The 2 was broken up into a 1 plus 1. However, you see this quadratic now? What two numbers add to 2 but multiply to 1? Two numbers that add to 2 but multiply to 1. Well, that's an s plus 1 and an s plus 1, right? 1 plus 1 adds to 2 and multiplies to 1. So what we have is we have 1 over s plus 1 squared plus 1. Okay. Now, that is something that if you look carefully at the table, go down here and look at this table, you can see, you see this sign, AT, okay? If A is 1 and S is replaced with S, well, what do we have here? We have an S plus 1 squared, okay? Then, what do we have? We have, let me just go back here. Let me see here. Yeah, this one is very similar. Okay. Let's go back to what we have here. It actually, in fact, if we look more carefully at the table, there is another item here. This looks like a multiplication. Oops, wrong one to bring over. Okay, it's in the table. Let me go here. Okay. If you look carefully, you see this s minus a squared. You have a b and a b squared. This is here. Okay, but you can get this equation using a property applied to, you see this sine AT? Okay, this is going to, if you use the frequency shift property, okay, which I will discuss in this lecture, then if you frequency shift the s, you shift it by a, you're going to get equation 21. But okay, we can just go into the table and use this equation directly. So let's use this equation. So, sorry, it's equation 19. Okay, this guy right here is what we have. So let me put this over here for a second. We have, you see right here, b is 1, a is minus 1. Okay, so if we go into our table, we can say from table, equation 19, b equals 1, a equals negative 1. Okay, let me just keep this right here. Okay, so if this is the Laplace, if we do the inverse Laplace, now we're going to take the inverse, Laplace of both sides. Now, okay, so we've got this guy and this guy. We've got it in a form that we can look in the table. So what we're going to do is, what's the inverse Laplace of s plus 1 squared plus 1? And here b is 1 and a is negative 1. And we go back to the table. Let me go and grab the table here. Let me double click it. Okay. Right? So look at equation 19. B is 1, so we have sine of t, and e to the negative, okay, because a is negative 1. So it's e to the negative t sine of t. Okay, so what we're saying here, let me actually grab this. All right. Let me go here. I'm going to grab this guy. Move him down. So what I meant to write here, actually more carefully, is I'm taking the inverse Laplace of both sides. So I'm doing Laplace inverse of Laplace of y is equal to the Laplace inverse of what's on this side. Okay? And what does that mean? Well, that's just y is equal to Laplace inverse of what's on the other side is e to the negative t sine of t. Okay? And that is the solution to the differential equation. It's quite literally that simple. Okay? So we can stop there. I think that's enough for this lesson. Okay, so I'm going to say I hope you enjoyed the lesson, and I hope it taught you something about solving differential equations using the Laplace transform.